Good morning, ladies and gentlemen, and welcome to this online session where we're going to talk about a blueprint for a 200 megawatt tower plant that fills the PV gap. And this has been an ongoing debate, I suppose, over the past few months, that what do we do once we have enough PV in the system, that it comes to a point where during the day, middle of the day in the summer, you get the duck curve, and we need to do something, with the time on the sides in order to fill in. At the system level, we need to just rethink and redesign how we're going to be doing the procurement of energy. Hence why we're here today, because there are people that are researching actively, how to use technologies that we already know and we understand well into improving them and optimizing them to become actually, if you like, partners with PV so that we can deliver 100% renewable energy in the system. So with me today, I'd like to introduce three experts that have been researching this for quite a while and that have a technological, if you like, proposal that they've been working on and that could actually do this for us. So I'd like to ask Alex to please introduce himself. Please unmute your microphone and introduce yourself.
Hello and welcome everybody. I'm Alexander Strück from Tractable Engineering in Germany. Tractable Engineering is a technical advisory company in the area of energy and water and is working in the renewable energy sector for quite a while. I'm here as a CSP expert in Tractable, working in CSP now for 25 and more years.
Excellent, Alex. Thank you very much for sharing all your experience with us today. Next, I'd like to ask Christian to please introduce yourself.
Hello, everybody. Also from my side, a very warm welcome. My name is Christian Schuber. I'm working for MAN Energy Systems. I'm here the head of new business. We are manufacturer of engines for power plants as well as for marine systems. We are doing turbo machinery, and nowadays we want to step into the CSP market with receiver systems. Thank you.
Thank you very much, Christian. And last but most certainly not least, we have Fabian with us today as well.
Hello and good afternoon, at least for local time, it's afternoon. My name is Fabian Gross, and I've been active in the solar industry for the last 9 years. And here at SBP, we have been developing solar technologies across the parabolic trough, heliostats, as you see in the background, and PV installations. Altogether, our technologies are used in more than 650 megawatts of installed capacity.
Excellent. Thank you very much, Fabian. So as you can see, you have three top experts that are going to be able to give to you know-how that is of incredible technical ability and skill. So I'd like to ask, the first person to speak is going to be Alex. So why don't you prepare your screen, Alex? And whilst he prepares the screen, I'd like to welcome people. I can see we have people from Mexico, from Chile, from Spain, from Germany, from Algeria, from Philippines even, so South Africa. You guys, thank you very much for being here with us today. Obviously, there is so much interest across the world. And even sometimes you guys are waking up at very, very early in the morning. So we appreciate that. Just a couple of housekeeping things before Alexander starts. Just one, we are recording this session, so it will be available and you'll be able to watch it again if you wish to. And also we will make the materials that you're seeing on the screen available to you, and we'll send them to you in an email and you can download them, okay? And that's it. Without further ado, Alex, go for it.
Thank you very much, Berlin. Hello to everybody again. I have the pleasure to show you today our work. What we call a CSP reference power plant. From this slide here, you can see how much people are involved in this project. So this is a group of 5 German companies sponsored by the Federal Ministry to work out a CSP plant that is not only Chinese, but that we can show that with common and new technology, you can build up a reasonable plan that can be used for your development and for your purpose when you're looking up for a new power plant in solar. We had some targets in mind when we started this work. Not only that we wanted to show that we are still in the business, We want to develop a solar power plant that is reasonable in the market. We wanted also to make it general enough so that everybody can make use out of it, so that it can be used as a blueprint for your project idea, to see that you can manage it and can even make it a real plant if you want. We also want to show and demonstrate some benefits and some options that can save cost and time when you are using our blueprint. So you don't need to start from scratch. You may use our plant and modify it to your needs, which we document, and then you can see if it is a reasonable project or not. Oh, so next slide. I would like to go to the next slide, but it's not working.
Okay, don't worry. Go again with the arrow, with the little arrows, the cursor keys. Sometimes it does get stuck. Now it works, yeah? Great. Technological problems.
Let me please start with the project share. You see from this simple graphics that we have tried to give our partners their main focus. But we do not leave them alone in this area. So everybody is speaking together here. So we are not leaving alone Steinmüller with the steam generation system, or Schleich-Bergermann with the Helios field. Everybody brings in his share and his experience into this power plant development. But on the other hand, you can see where the focus of some of the partners is. We have, of course, to find a starting point. And for this starting point, we need to make some assumptions and some basic conditions. First of all, we have to make assumptions and set some boundary conditions. That is obvious. We have to see what can we do and what is realistic. We have to size our plant in a certain manner. The next step we wanted to do is then to optimize all these starting points and to build up a system that makes sense, to build up the conceptual design for this, and to have an idea of our plans that we now can really optimize, and where we can see what is missing, what we have to change. And this will, of course, result in a design and in a conceptual layout for which we have to check out, is this bankable? Is this really reasonable? That is our idea with the CSP reference power plant. Of course, we have to think about it. We know that everybody wants to have renewable energy now. It's a good sell. And of course, one of the key options is solar. But we have market here and we have competition. Solar electricity from PV is very inexpensive. So tough to fight them with CSP power plants. Everybody knows that. But on the other hand, PV is producing at daylight. And we know that the CSP plant with the storage can produce electricity at any time. So whenever you need your power, we can provide it with a CSP plant. And in this case, we are looking for a CSP tower plant. We made, of course, our guess to the best fit. When should we produce our energy? To which point should we optimize our power plant? And we had some sets, and we find out that we should look for two key points. The simplest is to say, okay, when we want to compete PV or complement PV, night operation. Yes, we have to bring the power at night. The other point is, and that is what we see with the current towers on the market, they provide the power at peak season. So they stop operation somewhere around midnight. So these are two cases where we can build up a power plant. The next thing is, of course, location is everything. That is a key for a solar plant. We want to have a reference case. So what we are doing is build up a reference site. And we have a lot of discussions. What site should we take? Should we take the best site like in Chile? Should we take a challenging site where we have a lot of clouds or difficult meteorological system? But we think that the best situation is to take a site which is known, where you have good access to data, and we have some reference here. So for our purpose, the site in Morocco for Ouarzazate plant, that was a good option to say, okay, let's take the meteor data and meteorologic data for here, and let's take this as a starting point for the optimization. This site is also allowing you to modify the meteorological data and to see if your local file is well suiting. How big is the plant? We have a lot of numbers here. You know, the Spanish plant started with 50 megawatts. The first tower started with 17 megawatts. We have now the towers with 100, 110 megawatts in operation. We ask ourselves the question, should we improve? Should we go further? Does a 200 megawatt work? We know that there are limits in the optical path of such a plant. What should we take? And of course, we wanted to give the power at a certain time. So we definitely have to make a storage system, but how to make the storage system, how to size it. And of course, that is always kept in mind. We want to make a reference count, not something in the scientific area. So we have to convince people at the end. And for this, we have always to think again, what are we doing? Where should we go? And what is convincing? So we have to convince a client, we have to convince finances, we have to convince the environment or the people who later will live with it or work at it or will get power from it and buy the power from it. So always when we discuss about options and optimizations, we keep this in mind. And that is something you don't see on the slides, but it is a point of a background here for our development of this plant. But however, we always try to keep in mind and to take the state-of-art technologies. We want to build a modern power plant, we want to optimize it, and we want to use news development in our plant to have a very, very challenging situation here to tell them, okay, this is something for the future. I would like now to give over to Christoph to present some of the technical developments within this reference power plant. So for example, how do we build up our heliostat field, our solar receiver? How do we follow up later on in the turbine area? For this, I will give over now for Fabian.
Thank you very much for the introduction and the overview over our CSP reference plant project. Part of this project was the layout and design of the heliostat field, and the next 15 minutes are dedicated to concentrating the sun for the set CSP reference plant using the heliostats. So I will take you through the boundary conditions that constrain and define the layout of the heliostat field. One of the key ingredients you can play with as an engineer is the tower height. And we'll look at the influence of that. We examine the interplay between field and receiver, and in particular, focus on the flux density limits imposed by the receiver and aim point strategies that are taking care of that. This will lead to the heliostat field specification that we produce as part of this project and that you will be able to look at and use for your next tender. As was introduced by Alexander, we chose Ouarzazate as a reference location, as it has a typical latitude of slightly above 30 degrees north, right in the middle of the sun belt, and has a typical good irradiation. The other boundary conditions for the field are the capacity of the receiver, so how much power can the receiver take, and how large should the heliostat field be measured in the surface area of mirror. The storage in between decouples the activity from the heliostat field from the power block. So here you see the results from our study looking at the influence of tower height. On the right-hand side, you have to-scale representations of the tower heights we were looking at, with the black rectangle representing to scale the receiver dimensions. On the left-hand side, you find field layouts that follow from the different power heights, with the lowest tower leading to the broadest, most dispersed field, and the highest tower to the most compact one. These fields also differ somewhat in optical efficiency, but more to that later. I want to give you a perspective on how big or small these proposed fields are by comparing them to the already installed NUR3 power plant, also at Ursasate. So the 1.5 square kilometers of mirror area they were proposing here mean 14% more mirror area than in NUR3. While the field efficiency is improving when we move to higher towers, something else is also happening in parallel, and that is the increase in the capex, the cost for the tower installation and the piping within. And they grow over proportionally. That is something we need to keep in mind for an overall economic choice. From our colleagues from DLR, in collaboration with MAN, we got information about receiver designs. You find them on the first column here in the table. So we were looking at receivers that are relatively big and ones that are relatively small and something in between. So their surface area is changing, and with that, as they have the same power rating, the average flux density is changing. As they have different surface area, they also show different receiver efficiencies, thermal efficiencies. This is what you find on the left-hand side. And now the big green receiver has the lowest efficiency, while the small receiver shows the highest efficiency, thermal efficiency. But for a total power plant, you need to think heliostat field and receiver together, as it is also more challenging for a heliostat field to hit a small receiver. So the optical efficiency is higher for the green one and lower for the small red one. The crucial part beyond this little variation of field efficiency was how to actually run this solar part of the total power plant. And there we learned that we have two dominant loss mechanisms that we should look into more closely. And that is the low damping and high damping. The initial receiver designs that we had would only start operating above a lower threshold of 30% of nominal load and not going beyond 100% of nominal load. But already in the first days of January, you would see what kind of problem that would cause. It's quite easy to supply heat that is already interesting, but would be rejected by the receiver as the cut-in is so high. And on the other hand, even in winter, it is possible to supply more heat than the receiver could take. That led us in the consortium to change the pump design for the salt, allowing for lower cut-in and less low dump, and to have a close look at the high load situations and to see whether we can improve the utilization of the receiver. What you find here is on the right-hand side, an unrolled surface of that receiver having 8 facets. And the black line shows you how the salt enters cold in the north, travels through 4 panels, and will leave the receiver warm in the south. This same path you find from left to right in the left diagram. And what you notice is that the maximum allowed flux density is changing along the path. So if we now look at this situation and we build a difference between the flux that we have provided and the limits that we need to take care of, we find that this aim point strategy, a simple parametric one, is not good enough and leaves certain parts of the last panel with too much radiation. Therefore, we employed the control strategy that SPP has developed to address, in particular, these critical regions. What you see here is the dashboard of that controls system. On the top left, you see, again, the unrolled surface of the receiver, and you see how much radiation is impinging on that surface. All these little points there are aim points of these more than 30,000 heliostats that we have in the heliostat field. Top center, you find the difference between supply and demand. So white means you perfectly match the demand of the receiver. If it's turning blue, the receiver would like to have more power in this region. If it was red, it's more than the receiver has asked for. But what is really important is the criticality, as we called it, a measure for how close we are to the actual limits and how close we are in endangering the receiver to damage or destroy it. And if this criticality does not become positive, the receiver is safe. On the lower left side, you find a representation of the heliostat field. On the really left side, you find by color coding whether the heliostats seen from their own perspective are aiming a little bit to the left, then it's blue, or to the right, then it's red. And in the center diagram, it's about the height in which they aim. And the last diagram shows the internal working, the gradients in a landscape that drive heliostat aim points around. What we are now trying to do is to reach 900 megawatt incident power on a receiver that had only 780 as the design incident power. So it's about oversupplying 15% of extra power in a safe way. And for that, I'll start the animation starting from a random allocation of aim points, looking how the aim point control takes care of that and delivers power in a safe way. What you notice is how here a lot of white points move to the center. These are the outer heliostats with relatively big images that try to aim for the center of the receiver to have a high intercept. And it is the close heliostats close to the tower that do most of the vertical aiming and take care of providing enough power towards the higher and lower edges of the receiver circumference. Please pay extra attention to these corners here, where a higher density of aim points provide enough power in the third panel, but take care of not oversupplying the fourth panel. And as we see here in the criticality graph, is that we are able to provide 900 megawatts of incident power without violation of the receiver limits. So we were looking at a lot of different variants of tower heights, receiver designs, field layouts, and we try to compare them and find the optimal solution. What you see in this upper graph is mostly the loss mechanisms that helped us find the right solution. But please keep in mind that the offset that is underneath is quite big. So the green part is the power that is actually provided and is being used. So what we are talking about is an annual production of around 1.7 terawatt hours a year of heat that can be broken down to something like 1.8 gigawatt hours of electricity per day. That is 80% more stored electricity than in crescent dunes. So if you now look at the different variants, what we find is that for the big receiver, the medium receiver, and the small receiver, the effective production is quite similar. Whenever we increase tower height, that is along these columns, we do find a little bit more production, but most of that was going into the high dump. Therefore, we were developing this special solution that reduced the cut-in to reduce load dump and allowed for an overcharging of the receiver as we took care of the maximum flux that we were supplying and the limits. This leads us to proposing a relatively low tower with a medium receiver with a special pump configuration and the ability with a good heliostat control system to go into overload. I want to summarize with the heliostat specification that we are preparing in the project and that you will be able to use for your future projects. We've looked at all relevant parameters and used clear definitions. As we were working in the consortium, we have already figured out the difficult boundary conditions and interfaces that are between the systems. And we've consolidated how these systems work together. We propose a timeline to structure the actual realization of a project, and we're using the most official guidelines and test procedures that are available in the CSP world to assist you with the quality assurance and testing to get to a good heliostat field for your next tower project. We have shown that our heliostats can easily supply the flux necessary and needed by the receiver. Our heliostat field shows, especially at these large scales, low specific cost of less than 100 euros per square meter. The Stelio can offer a very high optical quality. You find the values there for slope and tracking error. And with the aim point control, we offer a fine-tuned operation. And the nice part about a heliostat field is that it is extremely tunable to your site, your tower height, your receiver, your meteorological condition. I'm looking forward to your questions and pass over to Christian. Thank you.
Thank you very much, Fabian. Can you take the presentation of the screen? There we go. Thank you. And Christian, if you can put yours. You guys send your questions through the Q&A box. We have a couple now. So obviously Fabian's presentation has given you some thoughts. So please don't hesitate to share. Just make sure that you use the Q&A box at the bottom so that it's easier for us to manage them appropriately. And Christian, the floor is yours.
Okay, you see my screen?
Yes, we do. Yes.
Perfect. So I will give you an overview in the next 15 minutes about, or we'll start with the overall design of the reference plant, and then I will step into the details of the receiver system. I will give a rough overview about the operating states, and then I will explain the receiver, the storage system, the steam generator, and also finally the power block. Okay, let's go. So here you see a proposal on the right hand side in that sketch for layout for the 2 times 200 megawatt peaker. So the diameter you see here is around about 250 meters. Of course, the heart in the center is the solar tower. And here you see the cold storage tank. So we have a 2-tank system, 1 cold storage tank and 2 hot storage tanks. And here in that box, you see the steam generator system. Target is, of course, to minimize the heat losses. So we arranged it as tight as possible. And the steam generator system is delivered by Steinmüller Engineering. And I will step here in detail later on, but we need per turbine 2 steam generator systems. So in that box, we have 4 trains in it. And then I can went over to the discharging side, so to say. Here you see the turbine house. We have 2 turbines in that case in it. Each turbine has its own ACC, And also here we try to arrange everything quite tight so that the heat losses are low. Here you see a raw water tank, demon water tank, water treatment, control room, and finally, of course, the gas-isolated switchgear, where we bring the energy then into the net. Okay. So far, so good. Now I want to step into the receiver details, the operating states. In general, we have, let's say, 5 states to come from solar tower off to solar tower operation. We start with the easiest mode, so to say, the tower off. So that means we have a long-term shutdown, e.g. Due to maintenance work or weather forecast with hardly any direct normal irradiance. So the solar tower, including the heliostats, is shut down. On the left-hand side, you see the cold storage tank, and here the hot storage tank. So the salt is in the tanks. And in the next step, we have to get into the salt circuit standby. That means the pipelines are preheated via heat tracing, and we can pump the salt via the inlet vessel back again to the cold storage tank. So this is the cycle holds everything on temperature, and in parallel, the receiver itself is preheated by some heliostats, which heat up the receiver system up to 350 degrees C. And if these boundary conditions are fulfilled and everything is in standby mode, the receiver is prepared for starting. So that means we can then drive the molten salt from the inlet vessel through the receiver. Then the vessel is pressurized, and we have here a control valve, and the mass flow is controlled, and we push the salt through the receiver to the outlet vessel and back again to the cold storage tank. And after getting reaching the boundary conditions, and we are ready for operation, then we can start the solar operation. So the temperature at the outlet of the receiver is controlled via the mass flow control. And of course, finally, the hot salt goes into the hot storage tank. Yeah. So now some words to the receiver itself. Here you see a picture of the receiver. The heat duty was already mentioned. So we have 700 megawatts of thermal power. The mean heat flux density is at around 540 kilowatts per square meter. We have an irradiated length of 23 meters. And the diameter is around about 19 meters. We have 4 serial panels in a row. These panels, or the salt flow velocity through the panels is 3.4 meters per second. So this results in the pressure loss, if you only look on the absorber tubes, of 6.5 bar. We reach a minimum part load of 20%. And the panel width is around about 7.2 meters. And for transport, we have divided them. So this is the reason that you see here 2 headers. Yeah. Fabian mentioned already, so we did a lot of optimization of the overall system as well as on the receiver side. So in some, there was 11 variants we were testing with our partner, the DLR. And the focus was, of course, on reducing the levelized cost of heat. And finally, with the setup I explained before, we reached now a longer lifetime by reducing the maximum heat flux density. So we started with 1000 kilowatts per square meter, and then we reduced it to 850 in the maximum. There are several points we did to reduce the investment costs. So in our case, we are only working with austenitic stainless steel. So we get rid of the nickel-based alloys in that content. The receiver is a small receiver. If we compare it to the 400 kilowatt per square meter variant, that means that we have also less welding seams and a very low pressure drop. And in general, it was already mentioned by Fabian, the target was reached that the solar field and the receiver are perfectly matched to each other to realize very low levelized cost of heat. Yeah. Now I want to switch to the storage system. So the storage system itself is more or less, let's call it a standard. We were here in contact with a few suppliers. We have, you see it on the right-hand side here, we were here looking for prices for the tanks itself. In our case, we have around about 50,000 tons of salt in the plant. So the costs for the tanks are around between 350 and 400 euros per ton. We have one cold tank and two hot tanks. The reason for going to two hot tanks is that we of course have to look on the wall thicknesses and so the stresses. And there was the decision to go to two tanks in that case. Second point, which you have to consider, considering the cost, is of course the insulation of the tank. Here you see the insulation thicknesses, which differ of course from cold tank to hot tank. And of course, one big cost driver is the salt itself. So the assumption here was 850 euros per ton for the salt and 150 euros per ton for melting up everything. Yeah. You also have to consider that we have the foundation in the price here and all the civil costs and so on. So including markup for the all storage system, we assume to reach around about 20 to 22 euros per kilowatt hour thermal. Okay, now let's go to the steam generator system. So discharge side. The steam generator system is engineered by Steinmüller. So now I spend some words for that company. Let's go first through the process itself. Here's the starting point of the feed water. We go into the economizer with 245 degrees C and 146, 48 bars. Then we go through the economizer. The preheated water goes into the steam drum. Out of the steam drum through the downcomer, we evaporate everything coming back to through the riser, and the saturated steam goes through the superheater and leaves it with 550 degrees C at 140 bar. In parallel, we have a reheater, which has inlet parameters of 37, 38 bar and 356 degrees C. And here we are also reheating up to 550 degrees C. The molten salt itself is entering with 560 degrees C. So outlet temperature of the receiver is 565. And we have here some safety, so to say. And we are leaving the economizer with 300 degrees C. I mentioned it already, one steam generator system provides finally 100 megawatts electricity or 240 megawatts of thermal power. That means we need two trains for 200 megawatts electrical. And as you see here, we have natural circulation boiler. So also here we had a lot of variants we discussed. And the focus was, of course, on cost optimization. and on OPEX. And in comparison to the one-through system, the advantage is that we have here a lower pressure drop. So the evaporator system has around about 6 bar and the reheater 3 bar. We have lower cost, and the disadvantage, so to say, is that in comparison to a one-through system, this system has a lower transient, so we can drive here 5 Kelvin per minute, where in comparison to a one-through system, you can go with 10 to 20 Kelvin per minute. But the decision was that it makes more sense because we know when we want to go when we want to produce, and so we can take the time in advance. The layout you see here now, I start again here with my mouse. So the feed water comes into the economizer. We have 3 economizers in a row to preheat the water. Afterwards, the water goes into the steam drum. From the steam drum, it goes to the evaporator, which is placed here below. And from the evaporator, here from the steam drum, finally, the saturated steam goes to superheater exchangers, which are fed in a row. And finally, the superheated steam goes to the turbine. And here for the reheater system, we also have 2 heat exchangers, 2 in a row. The heat exchangers are shell and tube heat exchangers, and as you can see here, we have one additional component. This is an electrical heater, which is used for startup and during standby to hold the system on temperature. Yeah. So far to the steam generator system. Then my last 2 slides. Finally, the words to the power block, and especially a bit the focus on, of course, the turbine. The turbine is a MAN turbine. So the maximum turbine we can provide is 200 megawatts electrical. Here are the live steam parameters: 140 bar and 550 degrees C. Quite important is, of course, also the air-cooled condenser. So the design exhaust pressure for our component is 135 millibar. So in minimum 100 millibar would be possible for operation. So the design case was night operation. That means 30 degrees C ambient temperature and an air humidity of 60%. And in that case, the own consumption of the ACC is 6.2 megawatts. And to ensure the minimum temperature in operation, which was mentioned with 245 degrees C, also during load changes, so in part load, this temperature in general would change. We have a bypass where we can preheat this water. Here you see the epsilon calculation for the turbine. As you can see, we have 3 low pressure preheaters, 2 high pressure preheaters for that system, for the power block. And the net efficiency is quite high with 41.6%. And I mentioned it already, we have also a good part load behavior. So we only have a pressure drop of 2%. That means at 50% we have 39.2% efficiency. And the reason therefore is that the power of the ACC can be reduced by speed control. And that leads to the high efficiency. The minimum load of the turbine is 25%. So also here we can go very deep. And finally, I want to say that also here the steam generator system, the steam turbine, and the ACC are perfectly matched to each other to minimize the levelized cost of electricity. So, and now I want to hand over again to Alex.
Thank you very much, Alex. Just make sure, yeah.
Thank you, Fabian and Christian. You have listened now to some key assumptions, key parameters, results in a technical way, in an extremely compressed form. We can proceed this for hours now here, but our time is limited. So I have to switch to a topic which is non-technical and is often, yeah, not to the fun of an engineer, but we have to speak about it. Yeah, come on. We have to speak about cost. Of course, you want to know if the power plant is reasonable and makes sense to think about it, or if you're speaking about skyrocketing high numbers. Thanks to DLR, I can present you here today some numbers and some outcomes of our estimations and assumptions. Let me start with input parameters. Of course, you have to price everything somehow. Most of you know that, for example, with models from Manuel, with SAM, we have some nice tables with numbers and input parameters for such a power plant. We made, of course, our own input data. So we discussed about certain numbers, about the experience of like MAN and SPP with their own equipment. And for that, we built up a quite huge data set of numbers and costs, which we used for a techno-economic optimization, especially DLR gave us here a lot of help. This cost is not fixed. So we are building a reference plant on some assumptions. We are not, can consider at this moment everything here. So you have to think about what is there really land cost? What is the water cost? What is the special taxes in your country? Stuff like this. Are you have a good access to financing? We cannot discuss it all, but at least we can build a data set and give you some input to see, okay, my numbers for my special condition for my power plant may change in this direction. Maybe you get equipment cheaper, maybe you have good funding. This is something we cannot consider yet and here. But we started with a complete set of data and make the calculations. DLR made a lot of optimizations. This is not only one run, one model. These are several models, several optimizations, and then you have to go back and back again. So it's a complex process. And of course, we other parties have our objections to some stuff, so DLR has to do it again and again. You see what we have done is at least the following modeling or the modeling optimization runs. For e.g., we have to see about the receiver overload, how to reduce it. We have to look for the optimal storage capacity, what you have listened to Christian. We have to think about operation modes, how to operate the plant properly, because this has very deep influence into our design. We have to think about operation times. So when do we want to start up our steam turbine in the morning or in the evening or in between? Things like this has to come into consideration for everything to get a proper output. And of course, the complete financial setup. When you develop a plant, you have to think about who will finance it, what interest rates you can get. Yeah, of course, somebody wants to earn money, so you have to consider margins and stuff like this. All this stuff has to be considered and built up in models, and we have to run it. Today, it's not the time to present this in detail. We will be here for hours. So let me simply offer you a sample here, one of my samples. We had made, for example, the typical annual yield. So we have to see for the site, how do we optimally run our plant? So when should we start? How much storage is necessary to the modes we have? And of course, we have to size this, the solar field again for this optimized mode. You see, again, we are speaking to each other. We have to see the capacity of the thermal storage now to make it properly working, that we don't waste any energy here. And for the table down, you can see there are 4 different modes now. So we speak about solar only. That is the typical plant with no storage, or in this case with 5 hours of storage. So that's what you know from other plants in the world. Then we going into the optimization that we say, okay, we will provide power only at nighttime. For this is storage of 13 hours to provide the power at winter. Then we think about the peaker situation. So we will give the power at the moment demand is highest in the evening hours. And you see, we have already think about, do we need 6 or 6.5 hours? What is the difference if we play in this small margin? This is all be done by models with DLR. And I can give you some key numbers with the next slide. So I think that is something you all wait for. What does this cost? We think that if we build our reference plants for a market that provides power when PV cannot. So making full use of the thermal storage system. You see the number here is 11 cents. That is a landmark for us. This is not the cheapest plant. That's not the question here. But what we want to tell is that if we build a reference plant for a targeted market, we are competitive. So if you want to have a safe and reliant delivery of your renewable power during the night, this is a cost you should consider. And you should also consider this is not the final cost. We cannot price in everything here. So for your plant, for your location, you have to think about additional costs. So things we cannot consider here. So simplest example, we always expect the flat land. So if you have to make some landscaping in front of it, this is not priced in yet here. So you have to see that this is also not only an optimum, but also an optimistic view. We have no obstacles here. You can see the differences in the different outcomes of the costs for our design. So you see that with the solar only plant with 8 cents, we are not so far away from the market price. That is something we have to keep in mind. Others has offered similar plants and similar sizes already for past projects in this range. So we are not so far away from that one. So we can offer here a plant that is placed well in the market. That's our bet now at the moment. We will not give you the final number for a full plant. That is up to you. What we give you is we have built up a plant and made a setup and conceptual design with the numbers we have at hand that will give this outcome. What we offer you is to take this plant for your project, to make the variations in all the ways you need to adjust to your seat, and let's see what the outcome then will be then for your specific project. And that is something what is our idea, to offer you a starting point and something where you can play with and see that it is a reasonable thing for you. We did not stop at this point. You know, such a plant needs power over day, and even though we have a steam turbine on site, the power needs for such a plant is so low that we cannot use our own steam turbine, or we waste a lot of power, or we have to give away the power for free, whatever the conditions will be. So we simply thought about what can we do. What is with the PV plant for our own consumptions, and what will be the influence on the LCOE? So you see, if we think about a plant with a delivery from PV plant 7.7 megawatts, we can bring down the LCOE up to 3% depending on the starting conditions. So it is a way to think about it. So this is a byproduct, but this is not the final adjustment. It is also a question of availability of land and stuff like this, or you buy the PV power from outside for a good price. But you see that you can play with all the numbers we have here, and that is something I want to show you. We had in between the questions why you are speaking about a tower and not about a parabolic trough. Parabolic trough would also be maybe cheaper here. Unfortunately, we had the idea in the very beginning when this project started, but unfortunately at that point, the German players went out of market. So we lose our experts in that area. And we focused now for the tower plant in this project, in this specific reference plant. But if it is worthwhile, we will discuss and we will implement the same thing for a parabolic trough plant. Let me summarize our plant. At the current moment, we have a nice 200 megawatt CSP tower optimized for the location of Wasserstadt. We have found that we should use a heliostat feed of 1.5 square kilometers. We have built up a solar system which uses a receiver of 700 megawatt thermal and a mean flux around 500 kilowatt per square meter. You have seen the process diagram from the power plant and the power cycle, even though barely to read because there's too much information in it. You know that we use an air-cooled condenser as it is standard worldwide now. We came to the situation for the nighttime use of the plant that we use the thermal storage system of 13 hours. And for that, we have a LCOE. Again, the hint is here, we are not fully with all costs in here, but we are at least in a starting point you can discuss and compare with others. At this point, I would like to make a reference to our publication, which will come end of this year, where we hope to give you the full information, the full set of numbers and data. We are collecting them now and bringing it into a form of report. We will also let you know how we will distribute this in the winter time when the report is free to use. In the meantime, of course, you're able to contact all of the partners for questions. And I'm ask you again, please let me know your question. Let us know your question that we can answer today, whatever is needed. Thank you very much.
Thank you very much, Alex. Unfortunately, we have run out of time. So I was just chatting here with Fabian and with Christian. There are 3 questions open at the moment. So since we are like 1 minute before the time, Christian and Fabian have kindly agreed we'll send the questions on to them so that they can answer them directly, if that's okay. And Alex and Fabian and Christian, thank you so much for sharing this very, very interesting job that you've done. And Alexander said that, the engineers, the price bores, is not so interesting, but I disagree. I think, I am really just a facilitator of content, but the question that I get asked more time than anything is, so what's the cost of this? So also discussing before the beginning of the session, we said to Fabian, to Christian, and to Alex that we will forward to you the report once this has happened, and it's available. Then we'll let you know that it's available so that you don't miss out if you wanted to, so that you don't forget. So without further ado, I think that it's time for us to say goodbye for now. So thank you very much, Fabian. Thank you very much, Christian. And thank you very much, Alex, for sharing this with us today. And as I said to everyone else, the recordings will be available. The materials will be available. We will forward information as soon as the report is ready. And the questions will be sent to the panelists also for them to respond. And thank you very much. See you next time.
Bye-bye. Thank you very much.
Thank you. Thank you, Alex. Bye.